Ok, on va reprendre. So, we now have a seminar by Professor Campoleoni from the University of Mons. Well, Andrea has been working on higher spin for many years, so he's an expert on higher spin, and he will talk to us about the applications of or aspects of higher spin massive gravity in the context of condensed matter. So,
thank you very much. Et avant de passer à l'anglais, je tiens à remercier le professeur Henneaux pour l'invitation et pour l'opportunité de donner un séminaire dans son cours. And now I switch to English. Today we are looking at non-relativistic limits, so the main topic of these classes, but of massive higher spin gravity. So here is something we are adding, something that I will try to motivate and explain to the basics topics that are explained, and I will also talk about condensed matter applications of these kind of structures. So, in particular, the goal of my talk is to try to convince you that looking at Galilean limits of gravity may have a useful application in condensed matter systems. And this is not a typo, so I put really the plural. I try to stress the plural because, well, you will discover during the course that there are many ways of taking maybe non-relativistic limits, and the important thing is that there are many theories that we may call gravitational. So it's not only Einstein gravity, and in particular I will focus on this class of higher spin gravity or higher spin gauge theories. This is not a condensed matter talk, and I assumed that most of the people in the audience have a more gravity-oriented interest. But anyway, I will have to frame the context in which I will talk about condensed matter applications. So I will start with a very quick review of the main example that I'm going to use, which is the one of the quantum Hall effect. So the introductory part will be very basic, but just to set the framework, to fix the notation, and then go on. So probably many of you are familiar with the quantum Hall effect, something that is maybe less commonly used, or maybe people are less familiar. I will focus on the effective field theory description of the quantum Hall effect, where these tools coming from non-relativistic limits of gravity are particularly useful. So, and in particular, to convince you of the importance, or at least usefulness of looking at non-relativistic gravity, I will review a link, a well-known link since 2013, of a link between Newton-Cartan gravity and transport properties of quantum Hall fluids. So this is one of the important works that kind of triggered the recent interest in non-relativistic limit of gravity. And then I will move more to my research, and it is try to use these limits, non-relativistic limits, to describe collective excitations inside quantum Hall fluids, and in particular I will try to present some relatively recent work relating these collective excitations to the limit of non-relativistic limit of higher spin gauge theories. So let's start with the basics about the quantum Hall effect. So that is really textbook material. So what is the quantum Hall effect, at least classically? The system that we consider, and we are going to consider in the following, just a gas of electrons that are confined in a two-dimensional plane with a magnetic field, with a constant magnetic field orthogonal to this plane. And a well-known observation is that if we have a constant current in the x direction, this induces a voltage in the y direction. So how can we understand this? This is really a textbook analysis. If we look at the force which on a charged particle in a magnetic field, we know that we have a force which is orthogonal to the magnetic field to the speed of a particle, and this is just the total force on a charged particle, where I also include a Drude-like term here. If I look at a static configuration in which there is no acceleration, we can see that the current, the electric current, the electric field are related by a relation like this. And due to the presence of this term, we also have some off-diagonal terms, where this omega b is just the cyclotron frequency that I stress here because we will see often in the following. So if I know the relation between the electric field and the current, I know the conductivity, that in this case is not a scalar, but is rather a matrix. And if I invert this matrix, I have resistivity. And essentially what we discover in the case of a quantum Hall effect, that we have a longitudinal resistivity, which is just constant. It does not depend on the magnetic field, and the transverse resistivity that grows with the magnetic field. So that is just simple classical physics of a gas of electrons in a two-dimensional plane. So what I recalled here is the classical Hall effect that has been observed more than 1 century ago. But more recently, in the 80s, people started to look at the same system at very low temperature and high magnetic field. And in particular, in the 80s, the first observations were around 2 Kelvin and with a magnetic field of 20 Tesla. Now we can do observation even with of this effect, even with lower temperatures and then lower magnetic fields. And the discovery is that the transverse resistivity, instead of growing on a line, actually present plateaus, and these plateaus are at integer values of this quantity there. So essentially, a quantum Hall effect shows is a macroscopic system that display quantization. While the longitudinal resistivity, instead of being constant, presents some peaks in correspondence where we jump from one plateau to another. So this is just an experimental observation. And shortly after, people went at even lower temperatures with very pure samples, and they observed that actually we don't only have integer plateaus, but we also have plateaus that the structure is much more complicated. And we may have plateau at these values of resistivity, where nu this time is a rational number. Not all rational numbers are allowed, but there are several types of fractions that can enter into this effect. And so the theoretical explanation of this observation is by now very well known, and essentially for what concerns the integer quantum Hall effect relies on the fact that if we put a particle in a magnetic field, in quantum mechanics the energy levels are quantized, something that we are familiar in many other situations. And since we are in a two-dimensional system, not in one-dimensional and not in one dimension, the Landau levels, which are these levels, these energy levels, are degenerate. And if I want to fill new Landau levels, I have to reach a electron density which is proportional to the magnetic fields divided by this elementary magnetic flux. And if we just do a kind of maybe naive comparison between the formula, the observed formula for the longitudinal of the transverse resistivity and the resistivity that we would have in the classical effect, we discover that the two agree if one fills precisely new Landau levels. So this led to an explanation of the integer quantum Hall effect, as a manifestation of the presence of this Landau level in the energy spectrum of a particle in magnetic field. Of course, this comparison does not explain why there are plateaus in the transverse resistivity, and the explanation of this factor is slightly more complicated because involved dealing with understanding the role of disorder in this system, but in a way or another, roughly speaking, the integer quantum Hall effect just relies on a single particle physics, essentially. The fractional quantum Hall effect also received a microscopical interpretation, although it's more complicated, because in this case, if we want to explain the fractional quantum Hall effect, interactions between electrons become crucial, and is the kind of result of strongly correlated physics of strongly correlated electron gases, which leads to very nice and interesting phenomena like the emergence of fractionally charged quasi-particles that are emergent excitation of this strongly correlated electron gas. So that is a very nice physics, but it won't be the core of the approach that I want to follow. Actually, in the following, I will change completely approach, and instead of trying to understand microscopically how to explain the integer or the fractional quantum Hall effect, I will change completely perspective, and I will try to write an effective field theory for the quantum Hall effect. What does it mean that I want to write an effective field theory for the quantum Hall effect? The idea is the following. So I want to build an effective field theory that captures the response of a quantum Hall of a given quantum Hall states to certain low energy perturbation. And what type of perturbations I will approach? But to begin with, let's start from the simplest possible one. So I will consider the electromagnetic field as a perturbation. So this means that I have my 2D sample, I have the orthogonal constant magnetic field B, and then I add an electromagnetic field on top that describes a perturbation. And the electromagnetic field could be, for instance, encode the electric field that was present in the review about the classical quantum Hall effect. So B that defines my quantum Hall states is always there, and I add on top an electromagnetic field. So that is the setup, and the goal is to write a partition function describing this system. But on top of this, I will add another crucial hypothesis, and the crucial hypothesis is that I'm considering energies low enough that I consider a system that only admits gapped excitation. What does it mean that the excitations are gapped? This means that if I want to excite an excitation of my system, I have to provide a finite amount of energy. So there are no excitations that can be excited with an arbitrarily low amount of energy, which means that if I am at energy below the gap, no propagating excitations can enter into my system. Which means that if I put myself at energy which are low enough, I don't see any of the possible low energy degrees of freedom of my quantum Hall fluid, and I can integrate them out. So what does it mean? This means that my partition function will be a function only of the external background, in this case the electromagnetic fields that I will use to perturb the system, and I can integrate out the microscopical degrees of freedom, whatever they are. So in the simplest example, you can think at a system of free fermions. I will integrate out the free fermions because I am at energy at which they do not play any role. But this type of approach will be applied also to the, it has been applied also to the fractional quantum Hall effect, where the microscopic degrees of freedom are not even so clear because they really rely on a complicated, strongly interacting physics. But whatever they are, if I have the hypothesis that I am below the gap and that they are gapped, I can always integrate them out and compute this partition function that will depend only on a mu. So why this effective action is useful? It seems like a stupid, not so interesting object since it only depends on the background, but the point is that if I take the variation of my effective action, so the effective action will be the exponential of the resulting partition function, this defines for me the response. So this is something that you're maybe familiar in quantum field theory courses, where when you compute the effective action, here there is a term which is J mu A mu, so you couple the source to the current. In more concrete terms, if I compute the variation of this object with respect to the electromagnetic potential, I will discover what is the electromagnetic current. And now there are two possible approaches. So either I compute this partition function because I know the macroscopic physics, or I try to guess it. And the procedure that we will take in the following is to try to guess it. If we want to guess it, we have to understand or to agree or what are the key properties of effective action describing the quantum Hall effect. So one key property for sure is that we need gauge invariance. So it's a function of a mu, so this function must be invariant under gauge transformation of the vector potential. And another property, very important property that will have an impact on what we can write is that we will demand locality of the partition function. So why locality? So there are various ways to try to argue more, and it can be done even more formally, but just to give you an idea. So the idea is that if we have a gapped system, essentially correlation function should decay exponentially beyond a certain finite scale, so which means that essentially my resulting partition function must be local. Or if you prefer, with a more high energy oriented perspective, if I suppose that my spectrum only contains massive excitations, this will never be able to go on shell at very low energy, which means that around to the value of momenta k equal to 0, all my functions should be analytical in momenta, and then I can take a Taylor expansion of my quantities, and this Taylor expansion in powers of a momenta in position space will be translated into an expansion in a derivative expansion, essentially. So that is the end result. So I hope that I convinced you that this kind of approach is sensible in this problem. And in practice, one considers a derivative expansion of effective action, where the terms that dominate the action are the ones with the lower number of derivatives. And now I just have to classify what are the terms that are gauge invariant according to the number of derivatives that they contain. In, say, 4 dimensions, the term, the gauge invariant term with a lower number of derivatives would be just the Maxwell action, which is a 2-derivative action. Here, since we are in 2 + 1 dimensions, there is an additional term that emerge, and it is this term here, which is called Chern-Simons action. And the Chern-Simons action is gauge invariant. It contains only 1 derivative, and it's something that I can write only in 3 dimensions. How can I see this? Because here you see that there is an epsilon tensor with 3 indices, and essentially 2 + 1 is the only dimension where I can introduce this particular term. The presence of this term, this epsilon tensor, as a disadvantage, if you wish, is the fact that this action is not parity invariant, so it's parity breaking, but it's not a problem because my system is parity breaking because I have my electromagnetic field pointing in one direction perpendicular to my 2-dimensional gas. So it's perfectly fitting all the symmetries of my system. And of course, that won't be my full effective action. Here will be correction. For instance, the first correction would be the Maxwell action, and then I will have higher derivative corrections, say, for instance, powers of the Faraday tensor that I can write. But this term won't dominate the physics at low energy. So at low energy, this is the term that will dominate the physics. Yes?
So the units are E equal H bar equal 1 here, right?
Yeah.
This is why you have 2 pi in the denominator.
I think so. So some H bar may be missing in my talk. So kept set to 1. Yeah, in this sense, yes. Yeah, no, thank you. And in this particular case, what I can do once we have identified my effective action, we can compute the variation of effective action with respect to the electromagnetic potential that has been announced before, and this gives us the electromagnetic current, so Ji, and also the component J0 that will be proportional to the density fluctuations of the sample. And the interesting observation is that we find find this relation between the current and the electric field. And you see that there is this ij epsilon tensor here, which means that the current is not aligned with the electric field, which is something that we have seen in the classical computation of the electromagnetic effect. We can even compare the previous expression with the current one, and we discover a relation between the transverse resistivity and this factor here that we have in front of the Chern-Simons action. And the two agrees if we make this, so essentially we recover the right transverse resistivity, provided that there is this identification between the value of k and the quantities that we have found into the system. And so this is already quite nice, that we find the right relation between the current and the electromagnetic field, but there is something more. Why there is something more? Because actually here when I told you that the Chern-Simons action is gauge invariant, I partly cheated, because the Chern-Simons action is gauge invariant only once the value of k is quantized. And that is something that one can verify. There are some boundary terms that may spoil the gauge invariance of the action in presence of boundary terms. So we assume here quantization of the Chern-Simons level, and the quantization of the Chern-Simons level directly transfer itself into an information of the quantization of the transverse resistivity. Yes, is a question?
The boundary terms appear, indeed, but then you assume that there is a boundary in you assume a certain topology of your...
Yeah, to get the quantization, yes. So, but I mean, here I'm just motivating a little bit the story. So I'm not gonna describe the details of why the Chern-Simons action is the level of the Chern-Simons action is quantized, but I just kind of sharing this information. That the level of the Chern-Simons action is quantized, and this can be directly related to the quantization of the transverse resistivity.
The electric field is the time derivative of AI, that's right?
Well, no, it's the usual relation. So the electric field is F0I. Yes, the derivative, the time derivative is the usual thing, while the magnetic field is obtained from the field strength, dualizing the field strength, exactly. And yeah, so what is kind of, I find nice here is that here we had very few assumptions on the system. The only assumption was that we have a gapped system, so that excitations are gapped and that we are in 3 dimensions. So these two informations allow to recover this information of the quantization of the transverse resistivity. And can we do something similar also for the fractional quantum Hall effect? The answer is yes, although the system starts to become a little bit more complicated. Why is becoming a bit more complicated? Because a new actor enters the action, so enters the game, and is this field small a. So now the effective action, we assume, the simplest way is to assume that it depends on 2 fields. So capital A remain my background electromagnetic field, which is really the object that I want to, that is really the background that I will use to compute the response functions. But on top of this, we assume that a dynamical U1 field emerge. So this dynamical U1 field is this A rho, and for the following, since I want to focus also on the gravitational application, so I will be agnostic on how it emerges. But the idea is that if we assume that fields of this type emerge into the dynamics of my system, I will have some universal consequences that will have an impact on the description of the system. And in particular, this assumption suffices to describe the class of fractional quantum Hall states, which are called as loafing states, which are the one in which the filling factor nu is equal to 1 over n. So it's a rational number, and is a specific class of rational numbers, which is related to the assumptions of this emergent U1 field into this system. But what is that let me stress that this emergent compact U1 field has this seemingly kinetic term, but it is well known that Chaire-Simons action does not describe any dynamics. Or if you wish, I can set up an action of this type, I can write the corresponding equations of motion, and the equations of motion are just the field strength of A of small a is equal to 0, which means that if the field strength is equal to 0, there are no wave solutions, so no dynamics here. So there are no excitations that propagates in this case. It is customary to call this kind of theories as topological theories. So topological theories have typically two features. One feature is that the action does not depend on the underlying metric, and the second feature is that there is no dynamics at all. So how is it possible that I add a field which does not propagate, so it's not a truly excitation, and still I obtain some modification on the physics of my system? And the reason is that topological degrees of freedom can affect the system at arbitrary low scales. And this is why this topological degree of freedom that enter into the system play actually a role. So here I won't enter into the details of what it's doing, but very roughly, if we take this action here and now we decide to integrate out capital A, what we obtain is an action of this form. So I go back to the Chaire-Simons action that we discussed before, but with a different factor in front. And in particular, this factor, this coefficient that we have put here, re-emerges after integrating out little a in this position, and roughly we can interpret it as saying that now the transverse resistivity takes this form, and we got indeed a fractional filling factor. I'm saying roughly because this is something that I can do on the plane, but is a little bit in contradiction with operation with the quantization of the Chaire-Simons level that I was advertising before. But there are more sophisticated way of checking that indeed this action describes the correct physics and brings a lot of interesting physics that is related to these topological sectors. So I won't enter into these details. This was the important message of this slide, is that to describe fractional quantum Hall states, we need an emergent U1 field. And now in the following, I will try to couple this U1 field to background geometry, and this is where the topic of this course will enter into the game. And I won't enter too much into the details, this very nice physics of topological system. So any question at this stage? No? Okay. So just to summarize, just adding this additional hypothesis of having an emergent U1 fields allow to explain already several phenomena, like the Hall conductivity is what we just discussed. It also explains why in this system one can interpret these systems as a system where conductivity takes place at the boundary of a sample, so with conducting edge modes. But as it is, this effective field theory, it doesn't capture everything. For instance, it doesn't capture all viscosity, which is something that we are going to discuss in a while, and it does not describe any the propagating excitations of the quantum Hall fluid. But as I'm going to discuss, we know that these fluids admit neutral propagating excitations. So this one is maybe less clear at this stage, but this is really crystal clear. So propagating excitations cannot be described with this action because, as I discussed, it's topological. There are no wave solutions, no way of describing something that propagates here. Now, the real question will be what we will have to do, because a priori here there is a plus dot dot dot. So a priori you can say, okay, that's maybe if you want to describe more, just add more terms there. So you can add a Maxwell term for both the background and the U1 gauge field. Why not? So that could be a solution. The point is that this is not the solution. So the relevant physics requires adding new ingredients. So describing this kind of phenomena. It's not enough just to say, okay, I continue my expansion of my effective action just using the bricks that I already put in my construction. So I really have to add something else, and this something else is what is related to gravity, essentially. Yeah, and so that was just this comment that I cannot just continue to expand the effective action. I have to do something more sophisticated. So let's start from all viscosity. All viscosity is another transport property of a quantum Hall fluid. The transport property means that there is a reaction to some background changes. And one way to describe this all viscosity dates back to the work of Wen and Z. And the idea is let's put my quantum Hall fluid on a curved background. And here curved background, the idea is really in the lab. So I just put it on a sphere, on a torus. I curve the two-dimensional surface where my quantum Hall fluid take place. So we are not discussing for the moment any four-dimensional metric. It's really special metric that on which I can put my background. So originally the idea was just to deal with a special metric. As you have seen this morning, you can also do more sophisticated things and covariantize the system. So you describe the system using a four-dimensional metric. So here I'm cheating a little bit because I profit from the fact that you just saw more clearly how to do. I introduced a special metric and I introduced a sort of covariant metric, but you have seen that the correct way to proceed will be to introduce a cometric, a degenerate cometric, and then introduce the structure bit after bit. But essentially, this is one of the structures that you have seen in a couple of hours ago, where you have this covariantization of the system, essentially. So once we want to covariantize this system, we have seen that you have to introduce also a clock form, which allow you to describe, which sits in the kernel of a degenerate cometric, and it could be convenient to also introduce what is called the field of observer, and the field of observer is just a vector which is orthogonal in this sense to the clock form. As we have seen just 1 hour ago, the field of observer is not unique because this equation does not have a unique solution, but we can assume that we fix the freedom to do this redefinition. We pick up a specific field of observer. So this is actually what has been done in the first work on the topic. And this operation of covariantizing the work of Wen and Z has been performed by Son in 2013, where he realized that the correct tools to try to couple or to study how we can put a quantum Hall fluid on a curved surface are the tools of Newton-Cartan gravity. And as I anticipated, this work kind of triggered a resurgence of interest in Newton-Cartan gravity. So we have a special metric, we can covariantize our system, and as we have seen, we can also introduce a connection. And here I'm putting it under quotes because it's not really the Newton-Cartan connection that you have seen earlier, but in general you can introduce at least a metric-compatible, a torsionless connection on your space. And here the terms in green are the ambiguities that has been discussed before. So these kind of conditions are not unique. And this term here, it was not present present in the previous presentation, but this was during the previous lecture, but this was just because here I'm using V to project on a direction. So what has been done in Galilean coordinates, where the coordinates had been fixed by choosing essentially a V that was essentially a special vector 0, 1, 1, 1. Now I'm taking the freedom of having an arbitrary V. And in the original work of Son, actually this term was not there. So it has been chosen this connection, and this connection is a connection that satisfies an additional condition, essentially a suitable projection of a covariant derivative of a vector V is equal to 0. There is a sort of compatibility also of the field of observers. But once I have the connection, I can also define a spin connection based on it. And here I call it an SO2 spin connection because it's a spin connection which is associated to the rotation symmetry of the system. And inside this definition, what you find are the field binds that were defined here. So I define the metric as being a contraction of these two objects that are called usually field binds, and the covariant derivative enters, which is based on the previously defined connection. Once I have my SO2 spin connection, I can eventually introduce a coupling of my quantum Hall system to the background geometry. So what does it mean in our context? So here I omitted the Chern-Simons terms for the capital A field. It's just we are introducing a coupling between the spin connection and the U1 connection that was this emergent field appearing in the fractional quantum Hall effect. And the spirit is the same. This is an effective action, so here there should be a plus ... but here in the following I will omit the plus ... So I will only focus on the terms at low energy that will be relevant for the discussion. And that is the when the action that here it has been shown how to recover it by profiting from the fact that we have a geometric structure, that we can describe a geometric structure covariantly. So once I have defined this coupling, I can proceed as before. So, for instance, we can integrate out the U1 effective field, A, small a, and look at the resulting equation of motion, or if you wish, in a more condensed matter language, the response equation. So I have a variation of my field A mu, I have a variation of my geometry, I see what are the variations that are induced. And if we look at the variation with respect to the background field, we recover equations that looks like the previous one, but with some corrections that depends on the geometry. For instance, here R is the spatial geometry of a spatial metric. So we receive, these equations receive some corrections, but you see at the beginning the term that allowed us to explain all conductivity before. And I can also look at the variation with respect to the spin connection, and it brings new transport coefficients and say this function which is called as a spin current, whose decomposition brings a coefficient which is called as Hall viscosity, which is a very strange viscosity because it is dissipationless. But what is independently of the details, so I promise not to focus too much on the condensed matter aspect, so not to give you a condensed matter talk, but to insist on the applications of gravitational theory in condensed matter systems. What is the message to keep is that introducing a geometric structure allows to access new transport phenomena. And we have seen in the lecture of today that there is a lot of freedom in introducing structures in non-relativistic theory. So the theory is not as rigid as relativistic gravity or Einstein gravity. So, for instance, already looking for torsion, for the analog of the Levi-Civita connection, so looking for metric-compatible and torsion-free connections leave already some freedom, and which means more objects with respect to whom we can take variations and try to explore new transport phenomena. And another things that you can do, for instance, is to introduce a torsion into the structure. And this is something that has been studied starting from Abanov and Gromov and many other people. And this gives you the possibility to access and describe with this effective field theory approach other transport phenomena. And what is the advantage of having this kind of Newton-Cartan gravity framework? The advantage is that this gives you an access to systematic access to the kind of tensor that you can introduce into your system, and then gives you a sort of classification of the possible transport phenomena that you can approach with your system. So I started with this approach, with this kind of physics for two reasons. One, because historically it's the first time where this kind of gravitational things, with these gravitational tools have been employed in a condensed matter context, and also because here we really saw an application of what you have seen in the course up to now. So this is an application really of gravity. So we are discussing gravity, its non-relativistic limits, and the possible applications of the geometric structure that emerged when you study this non-relativistic limit. But in the following, what I will do will be to discuss more the S that I tried to stress at the beginning, because there are more gravitational theories, and some of them may have useful applications into the study of condensed matter system. So, in particular, just to summarize, that when the action shows the role of geometry, but it still only depends on background fields. So my geometry is not a dynamical field, it's just a background geometry that I can use to compute a response function, and it does not describe any dynamics. On the other hand, it is known, it has been conjectured long ago, and it has been even experimentally detected, that quantum Hall fluids host collective propagating excitations. Of course, how is it possible? How is this compatible with what I said before? The fact is that these excitations are gapped. So you need a finite amount of energy to excite this energy. And here you see the energy spectrum of this excitation, which is similar to the one of the photons that you may have encountered while studying superfluidity. And this is one information, the spectrum, but there is also another information, which is the angular momentum carried by this excitation. So these excitations are gapped, are neutral, but under rotation they transform as a spin-2 mode, so, which means that they carry a non-trivial angular momentum. So the existence of this gapped excitation has been detected experimentally more than 20 years ago, but the angular momentum was trickier to detect, and this is a kind of very recent experimental observation in which people set up a system in which by light diffraction they were able really to measure the angular momentum of this excitation. So, and it is confirmed that quantum Hall fluids emit excitations carrying spin-2 angular momentum. And this excitation has been observed experimentally, and has also been derived microscopically. And in this context, they are called as a GMP mode, and how they have been derived microscopically. So people have access to wave functions describing these quantum Hall fluids, and they, based on the known wave function, they proved the existence of this excitation. Of course, this again is complicated physics because it's a strongly correlated system, and so often you have to rely on simulations to describe the dynamics of these things, even if there are some interesting relation with symmetry structure that I may just comment upon at the very end. But once again, the goal of this talk is not to focus on the macroscopic physics, but to see if it is possible to describe this kind of excitation from an effective field theory perspective. And so the goal will be to try to see how we can embed in effective field theory this kind of modes. And I will follow also several steps to go there. So first of all, I will review how this mode has been described using what is called a bimetric theory, in which we introduce another metric which is dynamical. And then I will move to another approach, which is one that allows us to make a generalization to the context of Eiger spin fields. So what is the idea of a bimetric theory is that aside from the background metric that we introduced before, we introduce a new dynamical metric, and which sense is dynamical, so there will be a kinetic term for this new metric field, but it takes the form of an additional metric. An additional metric with a condition, so, and if I introduce an additional metric, I can introduce some new internal, sometimes are called internal field binds and spin connection, following the same strategy as before. And the only constraints that we ask is that we ask that this new metric is unimodular. What does it mean unimodular? It means that the determinant of this new metric is equal to 1. Why this condition is imposed? Because this unimodular metric is supposed to describe the geometry of the excitations of a quantum Hall fluid, and the quantum Hall fluid is considered modeled as an incompressible fluid. So, which means if I impose that the determinant of a metric is equal to 1, I only consider deformation of my system that preserve the area. So these are what are called area-preserving diffeomorphisms. In the context of gravity, this kind of theories where the determinant of the metric is equal to 1 are called unimodular theories. And what do we do? The idea is similar to what we have seen before. We introduce a new structure, the new metric. We couple it to the U1 effective gauge fields. And the most natural guess is to continue to coupling it as we have done before successfully for the non-dynamical metric. But this time we also add to the effective action a kinetic term and a potential describing self-interaction of this object. So we see that this object interacts with a topological field and admits self-interactions. And you see, as I anticipated, that here we are completely changing the roots of the game. So we are not adding terms involving the fields that you already have into the system, but with more derivatives, but we are really adding new fields into the game in order to describe these excitations. Now, these terms looks ugly, but essentially, so here you have a metric G, a metric G hat. You can combine the two fields here, so you can write the connections that I shown before for these two fields. You define this object, and with this you get a kinetic term and a potential. And you see that this kinetic term is a two-derivative kinetic term. Yes?
What are the gauge symmetries you impose?
No, here no, because everything has been already written in terms of GIJ.
What are the constraints due to symmetries?
Okay, that is a good question because it's not completely clear to me, because one of the problems here is, for instance, that to my knowledge, for instance, it's not known how to recover the structure including the interacting terms as a limit of a gravitational theory, which makes the structure a little bit obscure, I would say. So there is for sure, this system is rotational invariant, that is manifest. There is also invariance under special diffeomorphism, and this is also manifest. The other symmetries are not not manifest in this kind of formulation. So that is kind of, we are leaving the part where things are really under control completely, and here there is a little bit of guesswork, at least to my current understanding of the problem. But the fact is that introducing this kind of action is sufficient to explain the observation for this kind of objects. And indeed, the rest of the talk can be seen as a sort of attempt to try to have a more systematic approach to understanding this kind of structure. So, where indeed, here there will be a bifurcation. On one hand, it will be interesting to better understand the origin of this interaction, and on the other hand, I will explain how this type of interactions, how this structure can be generalized to even higher spins. And maybe one remark before moving on is the fact that here we are not describing anymore with this biometric theory a real theory of gravity, because this kind of biometric theories, even if in this case we have kind of frozen one of the two because it's a background metric, at least in a relativistic context, are used to describe massive gravity theories. So theories where the graviton is not massless particle propagating to helicities in 4 dimensions, but 5. And in the case of 3 dimensions, it will be an object propagating to helicities. But that is one of the still open question marks, at least for me, so to better understand the structure of this kind of action. Other questions? No. Okay. So to move on, so here why I showed the biometric theory, because the biometric theory is again an application of geometry or gravity ideas to the context of the quantum Hall effect. Although, as you have seen from the discussion, the control, at least to my understanding, is not as good as the description of the background couplings in some papers. There was a trigger coming from gravity, in the sense that people looked for a geometric interpretation of these fluctuations, and they draw inspiration from these biometric theories that has been introduced to describe massive gravity. And now, is that the end of the story? We got an effective theory describing the GMP mode. This is great. There is a direct link with incompressibility and then with the area-preserving diffeomorphism, that is a symmetry which is also crucial in the microscopical derivation of this GMP mode. And we have also this nice geometry-like structure. But on the other hand, at least the algebra of area, the very existence of this algebra of area-preserving diffeomorphism suggests the existence of higher spin sectors corresponding to more complicated shape deformation. And also from a viewpoint of excitation themselves, something that has spin 2 is a sort of quadrupolar deformation of a sample. But why the sample should admit only quadrupolar deformation? We should have all possible types of multipolar excitation into the system. And then the next challenge is to try to understand how and if we can describe these multipolar excitations of the system. And to propose a road towards the generalization of this effective field theory, I will slightly change perspective. And one way of changing perspective is that I will take the previous action and I will linearize it. So we had this internal metric G hat, and I can so we can split the metric into a background flat metric plus fluctuations. And the fluctuations will be organized in a symmetric. I will consider fluctuations that are symmetric and traceless. If I do this, I introduce this rank 2 symmetric and traceless tensor Q. And the linearized kinetic term and potential taken together give me this effective action in terms of this field Q. And now I will kind of switch perspective, and I will show you how this action naturally emerges also from another perspective that does not involve adding this external metric into the system. And to present this other perspective, I will have to go back to condensed matter for a while and introduce the concept of nematic or p-atic phases, which is a concept that emerged in the study of liquid crystal. or liquid crystals. So what is the idea? The idea is that the dynamical part of an effective action that I just presented you can be recovered also using another perspective. And the other perspective is that this action is also the action that describes the system in the proximity of a continuous transition between an isotropic and a nematic phase. And the GMP mode emerges as the gap nematic fluctuation. But so what does it mean that there is a nematic phase? Which means that the system acquires what is called a nematic order. This is a concept that emerged in the study of liquid crystals. And what is a liquid crystal is essentially a state of matter which is kind of intermediate between a crystal and a fluid. So it has the property of a fluid, it can flow, but it has an internal ordering, or if you wish, it develops some preferred directions. In particular, a nematic phase is a phase in which there is a preferred direction, so which means that the system breaks the SO2 rotational symmetry, because you see, for instance, here in an isotropic phase, if I have a system of small rods, they can orient chaotically in all directions. If there is a preferred orientation, I'm going to break the SO2 symmetry of the system, but without breaking the translational symmetry as a crystal would do, because if you have a lattice, then we break the continuous translations to the lattice translations of the system. In this particular case, we just break the SO2 symmetry. How could be that this concept that is typical to describe liquid crystal play a role in the quantum Hall effect? So one possible way of seeing it is that we can look at our quantum Hall system, and we do a small quench of a magnetic field. So we just tilt the magnetic field for a while and we go back to the original position. And this kind of quench is breaking the rotational symmetry of the system. And this is a way to generate excitations that do not preserve the rotational symmetry. So this is why nematicity play a role in the study of quantum Hall fluids. So now these are just words that seems completely uncorrelated to the previous approach, but now I'm going to show you that actually is not the case. And the first way to see that there is a connection between the previous geometric approach and this nematic approach is to understand what could be the gauge parameter describing a nematic phase. So the key observation is that I can describe my system of small rods, that sometimes are called mesogen, by a collection of n vectors that a priori can point in any direction, but they can have a tendency to orient towards a very specific direction. So the most natural things could be, okay, how can I identify that I have a tendency to alignment? I could try to define a vector order parameter, but this is not possible, because essentially a rod aligned in a direction or the opposite of the same direction have the same probability. So if you wish, this system is invariant under rotation of an angle pi. And as a result, if I do an average over all the orientation of my rods, I get simply 0. So I will never be able to detect anything with a vector gauge parameter. On the other hand, I can define an order parameter, which is a symmetric and traceless tensor. And this idea dates back to Desgen, that introduced this concept to describe nematicity. And how I can define this object? I can define the average of a product of two of this direction minus its trace. If I am in the isotropic phase where there is rotational symmetry, this object just go to 0. So it has the right properties to be interpreted as a gauge parameter. But for instance, if I have a tendency to align along the direction y, this object will take this particular form. And in general, I can describe a nematic phase if there is an alignment along a specific vector with a certain direction. I can define a gauge parameter order parameter, that take this particular form. And since I am in 2 dimensions, this object will only have 2 independent components that I can put together to define a complex object. object that will be used in the following. And why here there is a phi divided by 2? Precisely because I want to have something which is invariant under shift by pi. So if I shift the angle by pi, nothing should change into the system. It should be completely equivalent. So you see that the objects that naturally emerged from the linearization of the unimodular metric, and something that was important that I should have stressed, the condition of determinant equal to 1 implies that the trace of the linearized metric is equal to 0. So that's I really looked at the most general fluctuation of the previous unimodular metric. The fluctuation of the unimodular metric has the same structure as the order parameter of the nematic phase. And indeed, we can even proceed further. So this idea has been pushed by Macheco and collaborators starting from 2013. And the idea is that we can identify the GMP mode with a fluctuation that would become the order parameter in the nematic phase. And then one can write an effective Lagrangian describing this system where there is our previous Chern-Simons action. There is this Ln, which will be the analog of the kinetic and potential term of a bimetric theory, and a coupling between the U1 fields A and this object QAB, which takes this particular form. It passes through this A mu n connection. So I can define a connection out of my objects, out of this kind of nematic order parameter. And the Ln, so the object that plays the role of the kinetic term, is what is called the Landau-Degen theory. And what it is just a generalization of a Landau-Ginzburg effective action to the case of the tensorial gauge parameter. So you can find structures which are close to the ones that you are used when looking at the Landau-Ginzburg Lagrangian. Why plus ... Because I'm focusing on terms which are quadratic here. So in general, if I really want to have, for instance, to drive a phase transition, I will have to add some interactions here, as in Landau-Ginzburg. But for us, what is important is just that these terms here that are the quadratic terms, because the idea is to identify this object with something that would become the nematic order parameter if I go into the nematic phase. And this kind of Lagrangian gives us gapped excitations, because if you compute the corresponding Hamiltonian, we clearly see that the system is gapped. So this is really a good candidate, at least to provide some gapped excitations that transform correctly under angular momentum. And indeed, we can push the identification even further, because if we look at the details of this Lagrangian that you can find, you open a book on liquid crystal, you can find this Lagrangian. Here is precisely what we got from the linearization of the bimetric theory. So there is really a matching between the two. And just to go a little bit more into the details of this matching, because it's important. So the nematic gauge potential couples to the effective action via this term that we introduced, where we have this composite connection AN. And this coupling just corresponds to the coupling between the internal spin connection and the U1 effective gauge fields. And the nematic gauge potential corresponds to the linearization of a GMP spin connection. And we can really identify the internal spin connection with something which is built out of the nematic fields Q, and similarly for the connection AN. So, but why doing all these, opening this ample parenthesis just to rewrite something that I already have written in terms of the bimetric theory? So the main advantage of the nematic viewpoint is that it clearly admits a generalization to any symmetry, so we can move from nematic to other types of ordering, or if you wish, it admits a generalization to tensor of arbitrary rank here, which means that it brings a clear way to generalize this effective description to excitations of higher spin. And that is what has been already proposed in the original papers there, and what we studied more in details in our work. And the idea is that tetratic means alignment along a direction, but we may have also different kind of orderings, and the simplest one is the tetratic, the following one. Why tetratic? Because there has been a proposal to preserve inversion symmetry, that all deformation should preserve inversion symmetry, and so here we just move to 2n-fold symmetry, so C2, C4, C6, C8. So if we move from C2, symmetries for rotations of pi, to C4, so symmetries or rotation of pi divided by 2, we ended into a system of this type, where there are two axes of an alignment microscopically for the system, essentially. And in this context, we have a tetratic order parameter, which is a rank 4 tensor, which is defined out of this kind of tetratic direction, which depends on phi or theta divided by 4, because we want to have identification under rotations of pi half. And the effective theory that we can write is very close to the previous one. So we just have our Chern-Simons discussed at length into this talk, plus a tetratic Lagrangian, plus a coupling between the tetratic sector and the U1 system. And to do that, we just have to define a connection in terms of these rank 4 tensors, and the Lagrangian describing the dynamics of a tetratic sector we just assume to be the Landau-Desgen-Lagrangian for this kind of ordering. Once again, just focusing on the quadratic sector. And this, as you can imagine, you can generalize to any P. So you move to CP symmetry. This will be described by a tensor of rank P, and you can generalize this kind of terms to any value of a spin. Yes?
What is the rule to construct a tetratic gauge potential? I mean, why 1/8 and -1?
Alors,
it has to obey some.
So the first part is because you want to write a connection, so they have the same coefficient there, and this is the way to write a connection. The last part, to be honest, is a kind of, this is conventional, it's kind of guessing work a little bit to, or you can test it in some microscopical model, and you can test that some terms of this type emerge, and this is the work that has been done by Macheco, so et al. Here we just took this kind of structure, and we focused more on this section, so how to recover this section there. So, and in a sense, this re-enters a little bit in all the kind of couplings that I've shown before. So it was A wedge omega hat, A wedge omega. So this part of couplings that you kind of guess for the structure. And of course, the coupling must preserve the fact that you must cook up something that transforms like a connection in order to make it compatible. And yeah, and then this is the tetratic Lagrangian. Now, the next topic that I wish to discuss is how all these constructions can emerge from a non-relativistic limit of something that is known in the relativistic context, and in particular from where this kind of theories come from. And in which sense I will do this? I anticipated before that we don't know yet how to derive a full Gromov-Sohn action, but we know how to derive the linearization of a Gromov-Sohn action. And then the following part of the talk will be to show what is the origin of these linearized actions. What is the spirit of the exercise is that clearly this is supposed to be a preliminary exercise to be able to then move to interacting theories and have a full control of the systematics of this kind of interactions. And I will discuss at the very end, but why this makes sense, because maybe you have heard the folklore is that Eiger spin fields cannot interact relativistically. This is true, but 2 + 1 dimension is not special only for electrons, it's special also for Eiger spins. So first of all, this kind of statements apply to massless Eiger spin fields already, even in Eiger dimensions. And second instance, this is not true in 3 dimensions, where these kind of fields do admit interactions, and people started to classify this kind of interactions. So we have a kind of virtuous combination of the fact that 3 dimensions are special both on the relativistic side and on the condensed matter, on the possible condensed matter applications. Of course, the applicability beyond 3 dimensions is maybe harder to export, but at least in 3 dimensions, we are in a very good footing to address this kind of problems. So the final goal will be to rederive the Landau-de Gennes-Lagrangian as a non-relativistic limit of a Fierz-Pauli action, or if you wish, of massive gravity. And in order to do that, let me first briefly recall what is massive gravity in this context. So the idea is that you have seen at length the Einstein-Hilbert action, and we can linearize it. And if we linearize the Einstein-Hilbert action, we obtain this action here, which is a quadratic action, because R mu nu here is just the linearized Ricci tensor. And this is just the form of the linearized Einstein-Hilbert action. And I can add, so we can add a mass term to the linearized Einstein-Hilbert action. This is something that at the linearized level is kind of safe and easy to handle. At the nonlinear level, it entails a lot of difficulties, but people know how to do even nonlinearly now, although it took a lot of work to try to understand how to add consistently a mass term to linearized gravity. But at the linearized level is easy. We just have to add this specific term here with this very specific combination. Here you already see the rigidity that creates problems when we move to interactions. And why we need this very specific combination here is something that is easy to understand if we look at the equations of motion. So the equations of motion of this action just take this form. So here you see there is h mu nu, I vary with respect to it, and these operators are self-adjoint. So these are the equations of motion. And what can we do is to compute a divergence and a trace of these equations of motion. In particular, if we compute a divergence, the first term here vanishes. Why? Because the vanishing of the divergence of this piece is just the linearization of the contracted Bianchi identity that you use to build the Einstein-Hilbert action. Or if you wish, you can substitute this and compute explicitly that the divergence of this object is identically equal to 0. But which means that taking a divergence of this object implies that the divergence of this object here is equal to 0. If we take a trace of equations of motion, where we have to open this R in order to compute it, but we got an identity of this type here. And what is interesting is that thanks to this very specific combination of these 2 terms in this term here, what we have in the first parenthesis is precisely the second divergence of the previous piece, which means that if this is to 0, also its double divergence is equal to 0, which means that this term there is equal to 0, and then the trace of the field is equal to 0. So if I don't write indices, it's because I have taken a trace. So the trace, which means a contraction with the eta tensor, is equal to 0. If the trace is equal to 0, I can substitute back here, and I discover that also the divergence is equal to 0. And all in all, this brings to the following equation, which is the first Fierz system of equations of motion that describe a massive spin-2 particle in any space-time dimension. Why this describe a massive particle? Because we don't have any more. Adding this mass term breaks the gauge symmetry, the symmetry under linearized diffeomorphism, which means that we have no symmetry anymore, no gauge symmetry anymore. In 4 dimensions, we have 5 degrees of freedom and 2 degrees of freedom in 3 dimensions that are described by these equations here. Now, next step will be to describe the limit, the non-relativistic limit of this equation, of the Fierz-Pauli equations. And here I just rewrote the system that I described before, just by putting explicitly the powers of C, because I want to take a non-relativistic limit of this object. And the key idea is to take my traceless field, so the field is traceless because this object is equal to 0, and decompose it in spatial objects. So this introduces a scalar, a spatial vector, and a spatial traceless rank 2 tensor. And then I can look at how boost acts on these objects, and what one discovers is that the transformation delta phi activates V, delta V activates S, but delta S is equal to 0. So this object transforms irreducibly under boost in the limit C going to 0. So which means that since it transforms irreducibly under boost, it gives a representation of the Galilei group in its own. And which means that these will be the objects that will describe my non-relativistic theory eventually. And the problem is that there are some subtleties that are related to the Bargmann central extension that has been discussed today. And the idea is that if I only do this, the limit is pretty poor. I have to do something a bit more refined to rediscover the Landau-Degenn action. And the idea is the following. So we introduced these rank 2 tensors, but we concluded that if I have a rank 2 tensor in 2 dimensions, we can combine its components to define a complex object. So in particular, we can take the 2 independent components of these objects S and define this Sn complex field. And once we have defined a complex field, we can rescale it by this phase. So this is just a field redefinition. So we introduce a phase by a field redefinition, but this field redefinition is crucial because thanks to the t-dependence inside my field redefinition, if I look at the transformation of the fields when C goes to infinity, I get something that contains the usual Lorentz boost plus an additional term. And these additional terms correspond to the Bargmann central extension. And long story short, eventually if I look at an action which is invariant under translation, rotation, and the new boost, including the central extension, there is only one unique answer, which is the Schrödinger action, which is equivalent to the Landau-Degenn theory that I introduced before. So the Landau-Degenn effective action is recovered as a non-relativistic limit. And this is a work that has been done already in 2018 by Berkshire, Rossell, and Townsend. And what we did was two things. So the first thing was to generalize this to Eiger spins. Actually, this structure that we have seen before, it's extend to fields of arbitrary spin. So we can describe the propagation of a massive particle of arbitrary spin by a Firth system that takes a form very close to the one that we have seen in the case of a spin 2 particle. We can do a similar decomposition in traceless components, and then realize that the traceless, purely spatial rank 4 part gives a representation of the Galilei algebra by itself. We can use it to define a complex object. We can perform the same field redefinition as before and take, with the very same consideration, we end up having a spin 4 Schrödinger action. And here you can say, well, written in terms of this complex object is the same action as before. What happens? Where is the spin? And the spin is in the transformation properties of these objects under rotation. So all these objects transform as e to the I s theta, but the value of s is different. So this is very similar on how you distinguish helicity in massless particles in 4 dimensions, essentially. And this kind of construction can be generalized to spin, to arbitrary spin. And then another question is that can we do more? So for instance, can we rederive everything from an action? And the answer is yes, although it's a little bit subtle. Subtle for 2 reasons. So reason number 1 is that if we go to Eiger spin, if we want to derive the Firth equation from an action, we must introduce a bunch of auxiliary fields. So we have to deal with auxiliary fields. But these auxiliary fields, we will see that will come to our rescue for some problems in defining the action. A priori, for the case of the Firth-Pauli action, you don't have to involve auxiliary fields because you have the Firth-Pauli action that I've shown you before. But on the other hand, we found it convenient to take a formulation in which we work from the very beginning with a traceless linearized metric fluctuation, and the price to pay is that you have to include auxiliary fields. We have been actually even more perverse because we worked in a kind of massive version of linearized unimodular gravity. So this is not the most standard way of presenting the action in the presence of auxiliary fields. Why so? Because we were driven by the idea that eventually we should go closer to the structure of unimodular gravity, to go close to the discussion of the bimetric theory. What does it mean that this is a massive version of unimodular gravity? You see that here we do not have a full Fierz-Pauli action, but we just have this term that sometimes is called Maxwell-like, and the idea is to do a sort of Proca-like construction. So the Proca theory is a massive version of a spin 1 theory, in which you can either describe it by adding a mass, so just to be concrete, let me write the Proca-Lagrangian here. So the Proca-Lagrangian could be just f mu nu plus a certain coefficients a mu. So here, if you are doing something like that, you are gonna break the gauge symmetry, and so you describe a massive spin 1 particle. But if you wish, you can also perform this shift. So you send a mu into a mu minus d mu phi, and you assume that the field phi transform like I think is m square lambda. And if you do this, you recover the gauge symmetry of the action. So you introduce an auxiliary field that makes the action gauge invariant. And you can generalize this to arbitrary values of a spin. So you write an action which introduces h mu nu, a vector, and a scalar, which correspond really to the degrees of freedom of a graviton. And you couple them by demanding that this action is has some gauge symmetries. So this approach looks very different with respect to the approach that I introduced before, but actually you can prove very explicitly, concretely, that it's actually the same thing in the same way. So you look at the equations of motion, you take traces and divergences of equations of motion, and you can use them to conclude the double divergence of H is equal to 0, and the divergence of B is equal to 0. Why this exercise is important? Because if you look at this expression here, you may realize that these objects, if we gauge away S, then the divergence of B becomes gauge invariant. So either the equations of motion allow me to gauge it away, or my gauge symmetry won't be sufficient to do it. So this is just to say that this is a perfectly legitimate description of a massive action principle describing a massive spin S particle. And this kind of action principle can be generalized to Proca-like action for particles of arbitrary spin. So you just have to introduce a bunch of auxiliary fields, order S auxiliary fields. You impose the existence of gauge symmetries. So here I'm using a shorthand notation where repeated indices mean symmetrized indices, but this is not the most important things. The most important thing is that here there is a sum over S, so we have a bunch of auxiliary fields, but there is a gauge symmetry, and the gauge symmetry fixes all the coefficients inside the action. So it has a very rigid structure of this action. So I have no free coefficients anywhere apart from an overall dependence on a factor m that describes the mass of a system. So it only depends from one parameter, this action. And then we can look at the non-relativistic limit of this action. So this it's a bit technical part that arrives at the very end of the talk. So my apologies for this, but just to conclude a little bit this part within this kind of subject. So let's see how we can take the non-relativistic limit of this action. This is another topic that will be approached during the lectures. And as far as I understood, so the idea is that the additional fields decouple in the limit c going to infinity, and so we remain only on something that depends on the field SAB inside h mu nu. So the procedure is a little bit complicated. Don't look at the details of the formula. Of course, it was just to give you an idea of what you have to do. But the key idea is what? So we take the same decomposition that we use to define the limit at the level of equations of motion, decomposition in traceless spatial components, and we inject it inside the action. So the action was already a bit complicated. If we do this, if we plug in this decomposition, it becomes even more complicated. You even have more terms, and in particular, you have this kind of structure. And here, everything it has been already rewritten in a complex notation. So a priori, I have a bunch of spatial tensors. I already combine all of them in complex fields, and there is this bunch of terms. The things which is important to notice on the other end, if I just do this, there is something very bad happening, because you see that we have powers of 1 over c and powers of c. So this is clear that in the limit c going to infinity, this action is going to diverge. So something we must do something in order to take a non-relativistic limit of this action. And the trick is to implement precisely what you have done before, plus some additional aspects. So the first next step is to introduce the same field redefinition as before, but this is even making things worse in a sense, because now we are introducing even oscillating factors of C, which are very bad if we want to take the limit, but some of them will play a role. But then the final important issue is that if we look after the field redefinition of the object that I called LV1, it takes this particular form. And since it is quadratic in this field U1, it allows me to integrate out U1. What does it mean? Is that I just write the equations of motion for U1, and these equations of motion for U1 will allow me to substitute U1 in terms of this current here up to terms that vanish in the c going to infinity limit. And substituting this solution inside the effective action precisely cancel all divergent terms. And eventually one remain with something that admit a perfectly well-defined c going to infinity limit, and in which essentially all the terms decouple. So all interacting terms goes to 0, and I remain only with terms which are quadratic. And the terms which are quadratic, if I look at the terms in Q2, very precisely gives back the Landau-Degen Lagrangian, because all these terms decouples. And so, what is the conclusion of all these excursus into the subject? So, one thing is that in the quantum Hall effect, we have seen that local order and topological phases can coexist. So we can have at the same time these nematic phases or p-atic phases and topological phases that coexist. And nematic and p-atic order parameters can be used to describing propagating gapped collective excitations in the bulk, where this p-atic characteristic is crucial to have to give to these excitations angular momentum which is higher than 2. And I must stress that these kind of phases has been conjectured from several angles but have not been detected experimentally yet. And it's also relatively complicated how to detect them, because you have to detect angular momentum. But for instance, people looking at simulations starting from wave functions observed the existence of these phases. They're even considering scattering of these collective excitations. And at least in the linearized regime, this effective action describing this collective excitation in agreement with the simulations can be obtained from the non-relativistic limit of massive Eiger-spin actions. And now that could be considered just as a curiosity, as a first step, but the idea is really to consider it as a first step to try to go beyond. Here I'm repeating something that I already anticipated. So the crucial message is that 2 + 1 is special both for electrons and for Eiger-spin particles, because in space-time dimension, we have massless and massive Eiger spin theories which are known, and in the relativistic context they have their own interactions which are highly constrained in the relativistic context, while in case of non-relativistics there is much more freedom. But of course I can compare with experiments, but it could be interesting to see the existence of a well-defined relativistic limit, non-relativistic limit. The emergence from a non-relativistic limit of a well-defined relativistic theory could be a criteria to organize the collective excitation. And another potentially interesting direction, although it's difficult to appreciate on the basis of the material that I put in this talk, is that introducing Eiger spin excitations into effective field theory may be a road to understand the role of area presenting symmetry in the effective field theory approach, where at the moment, at least to my understanding, is not manifest at all. So it's an important symmetry to understand the existence of this collective excitation from a microscopical viewpoint, but is very poorly explored from the effective field theory perspective. And so, thanks for your attention.